Hey guys, welcome back to the channel. In today's video, we'll be creating a Boid/flocking algorithm developed by Greg Reynolds all the way back in 1986. But since then, it has seen many applications and use cases, especially in the area of game development, where you might need systems for simulating bird behavior or fish behavior or any other swarming insect behavior. And the main reason I'm making this video, even though there are a great lot of resources on this particular topic, I kind of averaged out other people's videos like Sebastien Lague, the coding train, and even uses game dev, and I kind of tried to implement all that bulk into Unreal Engine and specifically C++. And I kind of ran into a little bit of trouble. Nothing major, but I thought it would be fun to kind of share my experiences in a live coding journey so that you guys would find something helpful and informative. With that said, let's get right into it. So I have a basic Unreal Engine level setup here, nothing major, just with a directional light, sky atmosphere, and a good old plane. The first thing we'll need is a Boid particle class. So let's go ahead and create that. Go to a Quantum browser, C++ classes, and right click, create new class. Make sure it's inheriting of type actor, since we'll be using get actor location and set actor location functions. And you can go ahead and create it. I've already created mine, so let's open up. And the first thing we want to implement within the Boid class is to define movement. And the way we do that is by using velocity and acceleration. Acceleration can come later on, but for now, let's just move the Boid in a straight direction. So to do that, let's come to a header file and define a public velocity. Once the velocity has been declared, let's come to our CPP and give it definitions. So in the begin play, let's define our velocity. The velocity is going to contain two components, the direction and a magnitude. So if you studied physics, you might know vector contains two components, a direction and a magnitude. And we'll first get the magnitude, or the direction, sorry, as the get actor forward vector. So the direction we are facing will be the default direction for the velocity. We'll also make sure to normalize that to avoid any conflicts. And for the magnitude, we simply need to multiply it with a speed value. So velocity multiplied equals a speed amount. For now, let's set the speed amount to be a constant value, so maybe 100, and that should give our velocity. So up to this point, we're only dealing with direction, although some might say we're dealing with a velocity of magnitude 1. Just ignore that for simplicity. Only at this point are we saying, okay, this velocity is direction and the magnitude, because we're explicitly giving it a magnitude. Once the begin play is defined, let's actually define a separate function to handle the movement of the Boid actor. Let's come back to Boid hedge, come back to protected, and it's going to be a void function, and I'll name it steer, and it's going to take in delta time. The steer function is actually going to have a vector of acceleration. So acceleration is the same thing as velocity, but simply think of it as the change of velocity. So the acceleration value will be calculated depending on the three rules of what makes a Boid flocking simulation, which are separation, alignment, and cohesion, which we'll get into later on, but for now we'll initialize to vector 0, so we don't change the corresponding velocity initialized in the begin play. Next, we need to add the acceleration to the velocity to see changes. But again, for now, we won't see any changes because the acceleration is vector 0. Delta time. And at last, we can simply set the actor location to get actor location plus velocity into delta time. You can put that inside another bracket. And if we build this, we should have a Boid that just moves straight forward, right? So let's come back to our content browser and come to the content and create a new folder for holding our blueprints. And then create a blueprint of type Boid. Select that and name it pp Boid. So if we double click that and create a mesh so we can actually visualize the Boid, let's create a static mesh component and give it a cone component, a cone mesh. Scale it down to 0.3, 0.3, and then rotate it in the forward vector direction. So that will be the y-axis and facing the forward vector. Compile and save. And now if we place the Boid in the world, we should hopefully see it move in a straight direction. Let's save everything, so if we crash, we can back up. And we are not moving at all. Let's go see what's the problem. So begin play get actor forward vector, get safe normal, multiplied equals 100, and then come down, acceleration into delta time, set actor location. So the problem is pretty simple. We're not calling the steer function. So let's come back into our tick method and call the steer function. A rookie error, but a simple fix. Let's build that again, and now we should see the Boid moving in a straightforward direction. Hot filter completed, and there you go. The Boid is moving all the way to infinity and beyond. So yeah, it's pretty cool. We have movement with such simple code. So that's why we are actually inheriting from the actor class. So let's come back to a Boid CPP and define a boundary limits. So we'll be actually having an area where the Boids can spawn, and if they go out of the area, they should come back into the area. Now there are different ways to implement this. If you watch Sebastien Lague's video, it's much more complicated, but then it's much more realistic, so to speak. It's much more desirable. But our implementation is just going to cut the buffer, or cut the area location, cut the location of the Boid and then bring it back into the area, but simply in the opposite plane, right? So if we have a area here, if the Boid leaves the area, it's going to come back from this side. So that's what we're doing here. So in order to do that, let's come back to Boid hedge and define another function. It's also going to be a void, and we'll give it a name stay in boundary, and it's not going to take any arguments. And within the function, let's actually define a current location. This is going to be get actor location, and we'll kind of modify the values within the get actor location. So let's perform some simple checks just for the x-axis, and we'll copy paste it for the other axis. So if get current location dot x is less than minus 2000, so this is going to be the square limit, we'll just set the position back to a positive value. I will do an else if check. The same thing, current location dot x, if it is greater than 2000, then we set it in the opposite direction. We'll put it at minus 2000. Now all we have to do is just copy paste the code for other axes, and that should give us a boundary limit. At last, we'll just say this set actor location call, location and current location. Now one thing I want to point out is we'll actually be working in 2D coordinates first, just to visualize and better understand the Boid's algorithm. But since we'll be future proofing it, I just went ahead and added the z-axis. But when we come to spawning the actors, I'll just limit it to the x and y coordinate. Let's build that and let's try to run this. And let's see if a Boid actually comes back into the area. Okay, I think I made the same rookie error here. I didn't actually call the function. So get back to our CPP, and yeah, I forgot to call the function. Let's come back below our steer function after everything has been calculated and stay in boundary. I keep forgetting to call functions for some reason. So that should actually work. Let's increase the speed so we can see better visualize it. I'm going to put 400. And that should be quite quick. Yeah, and it came from the other side. So it gets clips and come from the other side. So our boundary function is working quite well. And it should come from the other side, yeah. So that's fine. The next thing we want to implement is the entry point of our program, and that is going to be the Boid spawner function, which is actually going to initialize Boids into the world scene. So let's go ahead and implement that. Let's come back to our C++ classes, right click and create a new class of type actor, and then call it Boid spawner. And let's wait for the Unreal to kind of build the compile the project. So you might be actually tempted to kind of start writing your code here, but it'll give you an error. So you have to wait for Unreal to add the code to the project. So our class has been compiled. Let's come and reload the project. And then let's come back to our Boid spawner.h and include the Boid class. So include, call it Boid.h. And now let's come and define certain parameters for the spawner. Let's come back to public, create a separate public. Let's give a u property tag and edit anywhere. And we're going to call this int spawn count. I'm going to initialize to 30. And then let's come and define another u property tag, edit anywhere, and a t subclass of our Boid class, a Boid, and we'll call it actor or Boid to spawn, Boid, or maybe actor to spawn, actor to spawn. All right, and this will be of type a actor, so not a Boid, but we'll give the a actor the class of a Boid. And the last thing we want to do is the area of spawn, u property, edit anywhere, and then int spawn area. And remember, we are simply using a square, so we only need one side. Spawn area is equal to a default of, we'll keep it inside 2000. And lastly, one more thing we could ask is whether you want enabled center spawn. So if the spawn is originating from the world origin, so let's ask that as well. U property, edit anywhere, and then a bool value saying is center spawn, or maybe just enable center spawn, makes much more sense. And we set it to a default value of true. So once that is done, let's come back, or maybe we actually need to define a separate function. So protected, and we'll call it f vector get random vector. I will ask a double float range, double range minimum and maximum, and declare it. So let's come back to our get random vector and define the random vector. So f vector random vector And remember, I said when we're spawning, I want to flow the values between just x and y. So we won't be using the z-axis, so we'll initialize that to 0. But of course, we can come back and change this later on. And all we need to do is return the random vector. And that should have a random vector class. Let's come back to begin play to actually initialize the spawn. Let's run a for loop. And let's initialize the, or do the condition check. If enable center spawn, then the f vector spawn position. I'm making a lot of typos today because I just switched my keyboard and I'm getting used to it. Let's initialize to 0 and then come back to a spawn position. We can simply say get random vector between the spawn area, so minus spawn area and then spawn area, else spawn position is going to be an f vector 0. We could actually initialize to f0 vector and then do this, but why not? And lastly, we need to do a couple of things. We need to define a rotation value in order to spawn the actor into the world. So let's do that. It's going to be of type fRotator, and I'm going to name it random rotation. And fRotator, we can just come down and do it this way. We can ask fmat again. So this might seem a little bit odd at first. You might think this is a vector variable that's holding x and y and z coordinates, but it's a rotator variable. So it's including the rotation of pitch, yaw, and roll, and we'll be only controlling the yaw here. That's why I said 180, minus 180 and 180 for the yaw value. So on the z-axis, it'll be rotating in the 2D space, right? So let's keep that done. And lastly, we just need to initialize it. So we'll call the a Boid class, and we'll call it Boid, and then get world. We can spawn that right into the world. Get world, spawn actor. We'll give the type actually, and we'll call it a Boid. And then we need the actor to spawn. So actor to spawn, and spawn position, and spawn rotation. Random rotation. Okay, this should be spawn rotation. And now we should have a working rotation. Okay, so that should be it. One thing you might notice is that I'm not adding the Boid to an array, and we don't actually need to do that since we won't be doing distance calculations to every Boid in the frame. We'll be just checking Boids inside a certain area or region, and we'll be performing calculations on those Boids only, which will be coming to later on. But for now, let's just focus on spawning the Boids into the world. Let's build everything, and we have a successful build. Let's come and create our blueprint Boid spawner. We'll call it Boid spawner. Select and BP Boid spawner. Place it into the world, and make sure you give the reference to the actor to spawn. BP Boid, and then a spawn area of 2000 and a count of 30. Now, one thing you might be tempted to do in the code actually is come back, and let's come back to spawn header. And then here you remember I actually gave a T subclass of actor. This is actually kind of definitive in Unreal Engine ecosystem. Like if you're coming from Unity, you could just pass the actor class here and then you can put it in the editor, but you can't do that in Unreal Engine. If you're going to use an asset from your content browser, you need to give it the T subclass heading, right? So keep that in mind. So let's come back and check if everything is working. Let's save everything and let's remove our Boid from the scene and let's hit play. And yeah, we have a lot of Boids swarming around in the scene, and the boundary is also working for each Boid, so they come back from the area. Looks quite cool. And the enable center spawn is not working at the moment. I think I made a little bit of an error. Yeah, again, a silly mistake here. Let's just reverse the conditions and let's build that. And now we should have everything spawning from the center. Yeah, there you go. A beautiful sight indeed. Wow. And then they kind of go off the border and come back into the region. So that's quite beautiful. Let's do that again. So they go all the way out. And they have this beautiful dance going on. So yeah, that's pretty cool. One thing let's do is actually remove the plane a little bit down. Or the Boid spawner, maybe the plane. Let's make it a little lower. And also add a material to our Boid. Let's come to a viewport, static mesh, or a blue color. And then compile it. Let's try that again. Yeah, so that's much more contrasting. You can see what's going on better. So that's the first part of a program complete, and I could end the video here, but let's actually implement a Boid manager class that handles the parameters for each and every Boid. Let's actually come down to our C++ classes, and as always, let's create a new class of type actor and then name it Boid manager. Let's create that, and again let's wait for the Unreal Engine to finish compiling. And once the compilation is finished, let's actually reload the project and come to the Boid manager hedge and define certain parameters for each Boid. Let's come to a public again, create another public. This is going to be the velocity range for our Boid. Local flock radius. We don't have to worry about the local flock radius just yet, but I'll try to kind of implement that collision layer in this video. Once the parameters are set, you might be tempted to kind of just use the Boid manager and access the values right away from the Boid manager. But a good practice is to kind of define getter functions, so when you have manipulation of variables, don't have to access them in a different way. You could just call the getter function and you'll have the changed variable. So that's kind of a good practice to follow. So let's do that. And now once the build is complete, let's come back to our Boid CPP and actually use that Boid manager class instead of hard coding each value. So let's come back to our Boid.h and include the Boid manager. Boid include Boid manager .h. We should have that, and then come down and define a property. Let's actually put it in under protected and of type a Boid manager and a Boid manager. Let's come back to a CPP, and in the begin play, let's actually access the Boid manager. Now, if you've been following along from the previous video or the previous series where I did ray tracing in C++, I actually had a similar situation where I needed to access a class, and I made a really silly mistake, but it actually cost me a lot in efficiency, and that was to access a new object class in every iteration of the ray trace. So you can imagine if you're going like 1,000 depth, we'll have to create 1,000 new classes for each iteration, which is of course very ineffective and very costly. Another way I found is to kind of have a blueprint in the scene and then access that blueprint, or access the class from that blueprint, and so you can access the values from that class as well. So if you have like 1,000 boys running around the scene, instead of creating 1,000 new objects of class a Boid manager, you would just say, okay, everybody just find a Boid manager class whose actor is in the scene, and then we can access their value accordingly. So that's what we're doing today. So let's actually come to our CPP and define the Boids manager. So let's say Boids manager is equal to cast it into a Boid manager type or class manager, and then we'll be using gameplay statics. So let's actually include that. Let's come to our header file. We can say u gameplay statics, get actor of class, get world, and a Boids manager static class. That should be pretty much it, I'm assuming. So let's actually try to get the value from the Boid manager. So the velocity multiplication, we had a hard-coded value of 400, but not all Boids are going to be initialized at a single value. So we'll actually pick a random value between the ranges. So Boid manager minimum speed and the maximum speed. So get min speed and get max speed. Call it getters there, and that should actually do it. Once the hot reload is complete, let's come back to our blueprints and create our blueprint manager or the Boid manager. Select, name it BP Boid manager, and then place it into the scene and give it the parameters it requires. So our minimum speed is going to be at 500 and the maximum at 700. So it's going to be quite quick. And the local flock radius, again, we haven't really defined the usage, so I'm going to leave it at 0. And let's try to play this after saving it. And yeah, so now we can see, I think the difference between the speeds are quite low. Let's come back and try to put 1 at 10. So yeah, some Boids are really slow and some Boids are really fast. So now we have the get manager or the getter functions from the manager class working. This is going to be important later down the road because it really kind of emphasizes on clean code practices and increases the efficiency of the program. So let's close that, and as a closing note for the video, let's actually go ahead and implement the flocking radius. So in order to do that, let's come back to our BP Boid and let's define a sphere collision. This is going to handle the collision of the Boids, or this is pretty much going to be the important point in the Boid's life pretty much, right? So anything that enters a given area will be calculated against, and the acceleration is going to be defined based on this collision object. So let's actually increase the sphere radius to be 300, although we don't need it to be because we'll actually define it in the manager class, but just for visualizing, this is the area we'll be working with. So the Boid is this small, and if any other Boid comes within this Boid, they will be, or the area, they will be subjected to calculations like distances and the acceleration calculation, right? So let's compile that, save it, and come back to our Boid CPP or the hedge file and actually include the sphere component. So components, and you should have it. And then let's come back to our CPP, and in the begin play, let's make sure we have a sphere component. So and in order to do that, we need to obviously define or declare a sphere component value. Let's come back to protected and say u sphere component pointer and say local flock area. And the begin play, let's actually define the area. Local flock area is equal to get component by class use sphere component, and that should be it. Let's perform a check to avoid crashes. If local sphere flock area null pointer. So if it is not equal to null pointer, we'll actually set the area or the radius set sphere radius to be from the Boid manager itself. Calculate that and local flock radius or get local flock radius. Call the getter, and now we should have a Boid running around the scene with a collision component attached to it. Let's come back and play the scene, and let's pause the scene a little bit. So F8 and pause. Let's click on this Boid here and edit BP Boid. Let's check if it has a collision component. Yeah, and it does have a collision component 300, but I'm quite confused because we actually didn't set the manager class. So the local flock radius is 0. So if I set this to 500, let's edit this Boid, come back, sphere, and it's still at 300. So we're not actually getting the sphere component, it seems. So let's actually try to mitigate that. So ladies and gentlemen, I'm sorry to say that I've run into quite a bit of a problem, and this is because of a bug that has been persistent throughout the testing phases of my previous project. So the problem here is we can't actually set the collision component or the sphere collider radius after the begin play, it seems. So I have a code here. I actually changed the previous code when we have the get component by class, use sphere component, and then kind of try to do that. But let me try to build this. I actually forgot this line was in here, but the problem is you can't really. So if I play this, the radius doesn't actually change. So the local flock area has been the root here because we are creating a default sub-object. I actually had the local flock area initialized here before, but it seems it's not working. I'm not sure why. If local flock area, everything is working, there are no crashes, everything is initialized properly, but so I have to look into this. So by the next episode, I'll probably have this fixed. But for this episode, I think that's a good start. So thank you guys for watching. If you enjoyed the video, found the video informative, make sure to leave a like and consider subscribing. Also, I'm now on Patreon. Thank you for my Patreon supporters for making every video possible, basically. If you want to check me out on Patreon, you can follow the link in the description. And I also give you access to project files and source codes and other exclusive content which are in the making. So with that said, I'll see you guys in the next episode, where I hopefully have this all figured out.